Okay, welcome to class. Today is Thursday, and we are going to go over, you do have a two-part exam. So Unit 7 is Part 1 and Part 2. You're going to take Part 1 today. You're going to take Part 2 tomorrow. I'm going to review with you right now, and then I'm going to go over the details of how you're going to take the exam. It is 16 questions. Remember, with virtual learning, you're able to write everything down, and you can also use your notes on the exam. Know that the video that I'm creating right now that I will prepare and share with you will not be available during the actual test. So we're going to start off right now. With most things, I'll tell you when to write stuff down, and I'll tell you when just to watch. So please write this down in your notes. I'm going to write down examples of exponential growth, examples of exponential decay, and show you equations that are not exponential. So if something is exponential, it means that the variable x is in the exponent position. If something is exponential, the variable must be in the exponent position. So exponential growth, here's some examples. With all of these, the number in front was positive. The number or the rate inside of the parentheses was greater than 1, not equal to 1, greater than 1. And again, if it's exponential, the variable must be in the exponent position. Now, what about exponential decay? Each one of these is an example. Each one of these is an example of exponential decay. The number out front, representing that initial value, is positive. The number inside is between 0 and 1, not equal to 0, not equal to 1, in between those two values. And again, the variable must be in the exponent position. Now, students often get that confused. So, for instance, this is linear. This is linear. This is quadratic. This is cubic. In each one of these situations, the first thing I do is I look, where is the variable? The variable is not in the exponent position. The variable is not in the exponent position. The variable is not in the exponent position. So these are examples that are not exponential. So on one question of your test, they'll present you with a question. Let me just give you an example. And they'll say, is this an example of exponential growth, exponential decay, or not exponential? Is this an example of exponential growth, exponential decay, or not exponential? Again, variable is in the exponent position, so I'm looking at these two. It's positive, and the number inside is between 0 to 1. This is decay. The variable is not in the exponent position, automatically not exponential. All right. The second question provides us with a list of numbers, and it says write an explicit formula that models the geometric sequence above. So it's already sharing with us, yes, this is geometric, and they want us to come up with a formula. Really, this is a complicated way of saying come up with an equation that's going to model this. So what do we need to know? Well, when we have a list of numbers, we're going to refer back to this basic equation. You have a choice right now of either writing this down, because we will do another problem like it, or you can watch the first one and write down the second. This is the basic equation. So what two things do I have to know if I'm going to model this? I have to know the initial number, done, got that, and I have to know what the rate is. So with geometric sequences, we can figure out how to go from one number to the next, which is going to be done by multiplying or dividing consistently, by taking the second number and dividing it by the first. You may think, does it matter? Like, can I take the first and divide it by the second? No, it's the second divided by the first. So I'm going to flip right now into Desmos, and I'm going to do exactly that. I'm going to take 3/4, and I'm going to divide it by 3 divided by 16. and I can see the answer is 4. So what does that mean? That means to go from here to here, I'd multiply by 4, multiply by 4, multiply by 4. That's consistently, common ratio. You consistently go from one number to the next in a geometric sequence by multiplying, in this case, by 4. Okay, so my R is 4. I can achieve that by taking the second divided by the first, and I use decimals to do all the hard work. And the first number in this sequence is 3/16. So y equals 3/16. And then 3/16 times 4 raised to the x minus 1. A common mistake is students forget to do the minus 1. Remember, this is going to help us go back to the previous number and then take it times 4 to get to the next number. This is the equation. Now, what if we were asked to find, let's say we were asked to find the 8th number in the sequence. So the 8th number in the sequence, that's what I'm trying to find right now. 8th number in the sequence. So I'm going to rewrite this with, let's go with A at ends. It's the same concept, whether you use an X, Y, or you use A's and N's. So this is what it looks like. And now I'm going to replace the N with an 8. Now, a common mistake is, students know 8 minus 1 is 7. They know that part. But the mistake is that they often want to multiply first and then raise it to the 7th. Remember, PEMDAS, order of operations, says do exponents first before you multiply. So I'm going to do exactly that. I'm going to take 7, there we go. I'm going to take 4, and I'm going to raise it to the 7th. So I've taken care of this portion right here. Why is it to the 7th and not to the 8th? Because 8 minus 1, the 8th number in the sequence, 8 minus 1 is 7. And now I'm going to take it times the quantity 3/16. So this is my amount. So what does that mean? So more importantly, what does that mean? That means here's the first, second, third, fourth number in this sequence, 5th, 6th, 7th. I know that when the input is 8, which means the 8th number in this list, the answer or the output is 3072. So this is still like question number 2. Still strongly suggest you put this in your notes. If you didn't put the first one, put this one in your notes. The question is going to ask us to write the explicit formula that models this geometric sequence, right? The explicit formula. So whether you choose to use x and y's, and it looks, whether you like the x and y or you like to use the n's, they're the same. When I grade it exactly the same. So there's 2 things I have to know. I have to know what is the first number in the sequence, easy enough, that's 2. And I have to know what is that common ratio. That means how do I get to one number to the next. Now, some of you can just do that by looking, but if not, you always take the second number and divide it by the first. 8 divided by 2 is 4. Let's check. 2 times 4, good. 8 times 4, good. Okay, so R is 4, A sub 1 is 2. So what would I give you credit for? I'd give you credit if you put 2 times 4 raised to the x minus 1. I'd give you full credit for that. And full credit for 2 times 4 raised to the n minus 1. Full credit for that. All right. Now I want you to find what is, let's go with, what is a to the 7th. So I'm going to give you 30 seconds right now. I'm going to press pause on this tape. When we rejoin you, I'd like you to press pause too. Go into decimals, practice actually plugging this in to get an answer. And 30 seconds. So the seventh number in the sequence, this is 1, 2, 3, 4, 5, 6, and 7. So when the input is 7, the output is 8,192. Common mistakes, what do I see? Well, common mistakes would be, I see that students forget to put the -1, or when they're in a hurry, they're trying to find the seventh number, so they simply raise it from 4 to the 7th and then take it times 2. Remember, it's 7 minus 1. This is the third type of question. I'm going to ask everyone just to watch this one. Unless you're really quick at writing things down, just watch. Know that the second problem I'm going to have you write down as I go through it. So we've been working with geometric sequences. That's a list of numbers you get from one number to the next by either multiplying or dividing by a common ratio, okay? Notice that they're separated with a comma. This is a geometric series. So same numbers, 2, 8, 32, but now instead of being separated by a comma, they are separated by an addition sign. They're separated by an addition sign. So what this particular question wants us to know, and let me use the exact same wording if you just give me a second here. Thank you for your patience. The exact wording is find the sum. Find the sum of the geometric series. So geometric series, if we were not in virtual learning, you would have to memorize this formula. This is the one thing I would like you to write this down. If you're not writing anything down, please put at least this formula down right now. So S stands for sum of how many numbers in a row. It's the first number times 1 subtract the rate, 1 subtract the rate. Now the only difference between the top and the bottom is up here above the R, we put an N. So A sub 1 represents the first number in this series. R represents how do you get from one number to the next. In this case, we are multiplying by 4. And I can achieve that in the same way as we did a sequence. Take the second number divided by the first. So my R is 4. N represents how many numbers in a row do I have to go from here to this one. That's what we have to figure out. So for instance, I know this is the first number, the second, the third, the fourth. I don't know what this is. I need to know what number is this in the list before I can do anything. There's a couple ways to do this. I'm going to go over it the longer way, but it seems like the least complicated way. So I'm going to start by knowing that I start with a 2, and I consistently multiply by 4. I want to know how long does it take to get to this 32,768. So again, I start with a 2, and I consistently multiply by 8. So there's the first term in the series, multiplied by 4. So the second number in the series is 8. Notice I have two numbers up here, and this is the answer, or the term, that's the second number. Take it by 4 again, that's the third term. Fourth, fifth, sixth, seventh, eighth. Okay, so 1 starts with the first, and we consistently multiply by 4 in this case. So 1, 2, 3, 4, 5, 6, 7, 8. It takes 8 times to go, 8 terms in that sequence. So if I come back here, I know this is the 8th. Now why do I need to know that? Because this says add up the sum of this geometric series. So I need to know how many are in here. There's a total of 8 terms, or 8 numbers. So this n now becomes an 8. So S of 8, the first number is a 2. 1 subtract, 1 subtract. To get from one number to the next, remember I'm multiplying by 4. And I want to know what is the sum of the first 8. So I'm going to plug this in. I'm going to plug this in right now into decimals. And by the way, I have found that when I plug it into decimals, I make less mistakes when I actually multiply by this first number at the very end. And does it matter if I multiply in front or at the end? Well, remember, multiplication, it doesn't matter. So multiplication, I can go 1 times 2 or 2 times 1. 1 times 2 or 2 times 1 is the exact same thing. So whether I multiply them in this order or the other order, I get the same answer. Okay, plugging it in at this time. So I start with the numerator, 1 subtract. I have to use parentheses, that is the key. 1 subtract 4 to the 8th, divided by 1 subtract 4. And now I'm going to use the arrow on my keyboard to move behind it, and I'm going to multiply by that first number. What does this quantity mean? 43,690 means if I add up the first 8 numbers, here in this specific geometric series, this is what the sum would be. This is what they would add up to be. So continuing on with this type of problem, we're just seeing another example. The suggestion is going to be that you do write this down. The directions will be again to find the sum of this specific geometric series. Remember, this is the formula that I'm going to be referring to. I need to know the first number, got it. I need to know the rate to get from one number to the next. It's called, remember, it's called a common ratio, and I can take the second term or the second number divided by the first number. In this case, I get 4. So I already know that it's S. I'm going to just do a really light N so I can write over the top of it. The first number is 5. And then my common ratio is 4, so 1 subtract 4. Now what I'm missing out on is this N. I need to know, how do I go from here to here? How many numbers do we have to do? Okay, here we go. 1, 2, 3. Okay, so again, I'm going to go over this the long way. There's sometimes a quicker way, but I have felt like in the past not as many people catch on. So in this case, I think it's being virtual. I think it's better to go through the longer process that's a little bit simpler. I'm going to start with 5. That's the first number. And then I know if I multiply it by 4, I get to the second number, not 44. So here's the second number, 20. How do I know that? I can just check over here. Notice that 20 is next, and then 80 should be the third. So I continue to multiply by that common ratio. Notice 80, so there's 3, 4, 5. I'm going to make sure I've counted it correctly. So I have 1, 2, 3, 4, 5, 6. So I'm up to 6, 7, 8, 9. Okay, it takes 9 different terms to get here. This is the 9th term. So once I know how many terms does it take to get to this final number, now I get to replace the N with that number. And I'm going to do this in decimals, but remember, my suggestion is always to put this number in back. I think less mistakes are made when plugging numbers into decimals then. So I'm going to come back to decimals. On top I have 1 subtract 4 raised to the 9th divided by 1 subtract 4, and then behind it I'm going to do a times 5. So I'm going to write down this number, and then let's talk about really what does that mean. This means for this particular geometric series, if I add up the first 9 numbers in this geometric series, it would be a total of 436,905. Okay, next we're going to do the same type of concept, but we're going to start adding. Okay, Aaron went to ASU. Aaron used to be a student at Trevor Brown. Aaron was involved in cross country and track. Really, he enjoyed working out. He enjoyed staying fit. He goes to ASU, and he is so overwhelmed with academics and meeting new people and a transition from life from living at home to living in college that he has forgotten to stay balanced as far as working out and trying to be healthy. And so while he is home over winter break, he's decided, I need to start running again. And he happens to live close to Eloso Park. Now he knows he doesn't want to start a routine that seems hard to continue. So what he does is he says, all right, I know I could do this. And on the first day, he starts on a Monday, he says, I'm going to run once around Eloso Park. So he starts, runs once around, and that's it. Tuesday he comes in, he runs twice. Wednesday he comes in, starts the morning off, and he runs 4 times. Now if he consistently does this, following this pattern, all the way through Sunday, so for 1 week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, I want to know by Sunday what is the total amount of laps in this particular week that he has run around Eloso Park. So to do that, again, I'm saying the word total, not just on Sunday, that's where the misconception is. In total, how many laps does he run around Eloso Park over those 7 days, which is 1 week? So I'm figuring out the sum. So I'm going to write down the general equation once again. What do I know? Well, I know the first number is 1. Now, how do I figure out the rate? Well, I always take the second and divide it by the first. So it looks to be 2. 1 times 2 is 2. 2 times 2 is 4. Okay, it looks good. So the rate is 2. It's doubling each day. Now, how long is he going to do this? He's going to do it for 7 days. 1 week is 7 days. And this is what I plug in to Desmos. So I already have it up here, which makes it pretty easy. I get just to switch some of these numbers here. And in 1 week, if we combine the total number of times he has run around Alosa Park, in 1 week, Aaron will have run 127 times around the park. Okay, here we go. We're going to talk about Jerry. Now, Jerry has signed up, and he is planning to go to boot camp in the summer. So over spring break, he makes the decision. He says, I got to get in shape. I know I'm going to boot camp in about 3 months. I want to be in my best shape possible, and I need to start doing sit-ups. So on day 1, he does exactly 5 sit-ups. On day 2, he has increased it to 15, and on day 3, he has increased it to 45. I want to know, after 10 days, what is the total number of sit-ups Jerry has completed? After 10 days, what is the total number of sit-ups that Jerry has completed? I'd like you to press pause. Give yourself about 30 seconds to see, not can you plug it into Desmos, but can you create that equation that we will eventually put into Desmos. Go ahead, please. Press pause. Then press play again once you have the equation. So here's what I do right away. I go, do I know the first number? I do. Can I figure out the rate? We'll take the second number and divide it by the first. 15 divided by 5 is 3. Times 3, yep. Times 3, yep. Okay. And I want to know the first 10. If I add up the first 10, so I'm going to plug this into Desmos. Oh my goodness. If this were true, this would mean that Jerry, after a total of 10 days, would have completed 147,620 sit-ups. Crazy. Okay, a town currently has 1,200 people living in it. It is expected to quadruple every 3 years. After 18 years, what can we expect? What can we expect the size of this town to be? Now, okay, so when we're looking at this, remember that I'm kind of using my own variables. We have a total amount. We have the initial value, and you could use a sub 1. We have a rate inside, and then up top, remember, we have a fraction. I'm going to put an O here. This means occurrence. How often does this rate occur? And remember, the number on top is going to correspond to the total. So whenever you get a total, it's going to relate to a certain amount of time. Again, the number on the bottom relates to how often does this rate occur, whether it's an increase or decrease. And the initial amount is up front. So what do we know? We know the initial amount is 1,200. We know it's going to quadruple. How often? Every 3 years. The occurrence is every 3 years that it quadruples. Now, it says, what is the total after 18 years? So again, this 18 is going to relate to the total. So I press 18 up here. I want to know what is this total, and now I can plug it into Desmos. Now in Desmos, I also know that 18 divided by 3 is 6. If you didn't know that, you could type in 18 divided by 3. It would be okay. So I'm going to come over here and do 1,200 and 4 raised to, then let's pretend you were not great with your division. You want to make sure you did it right. So there's what we have. Oh, excuse me. And so again, I just want to make sure it looks good, So what does this mean? It means the population of this town we can expect to be approximately 4,915,200 after, here's the key, you have to write a sentence, we can expect it to be that much after 18 years. That's the key. This much after 18 years if we assume that it quadruples every 3 years. Remember, this video will be available for you just for the first part of class, but not during testing. We're going to say that you got lucky. We're going to say you're 18 years old, and you decide to go with Grandma to the casino. And we're going to say you got really lucky and you won $500. And Grandma's really a saver, and she says, you know what, the best thing you could do is just simply to invest that money and not touch about it and forget that you even have it. And so you're 18 years old, and you're going to work until you're 68. You're going to retire at 68. Now, what's the difference between 18 years old and 68? That's over 50 years. You're going to just invest this money, and you're not going to touch it. You're not going to add to it. You're not going to take away from it. And if we looked kind of at the cycle of a stock market and investing money, it looks something like this. It's going to go up and down. You always hear about the stock market going up and down, but in general, it continues to have a rise. Now, there's going to be points where it goes down and then it goes back up higher, but again, in general, it's going to be rising. So, I want you to think to yourself right now, what do you think that $500 will turn into? What do you think it will turn into after 50 years? And I am going on a rate right now that it's suggested. It suggests, this is what the rate suggests. It suggests that your amount that you invest will double every 11 years. That's what they say. Every 11 years, if you invest in something, something that's not too conservative, something that's not too aggressive, just middle of the line here, every 11 years it will double. Okay, well, we want to know after 50 years, how much is this worth? So let's go here. We got an initial amount of 500. The rate is doubling. The rate is doubling. Now, how often? What is the occurrence? It's doubling every 11 years. We want to know what is the total after 50 years. What is the total after 50 years? Okay, so you have never touched this money. You're now 68 years old. You went from 18 to 68. You haven't touched it. Let's see what this could be worth. 500, and we're going to go with it doubles. And how often does it double? 50 divided by 11. And, oops, excuse me, I wanted to bring that down there. And we can say that it is very probable, and I know I didn't put cents involved here, but it's very probable that you went from owning $500 and it has gone all the way up to $11,675 if you never touch it upon retirement. That's what it would have turned into. Okay, and by the way, this is real life. This is something kind of a rule of thumb. Does it happen for everything? But no, it's kind of a rule of thumb. Okay, we're going to do the same thing now, and we're going to talk now about half-life. So the last two problems we've increased, right? Is we've had exponential growth. We're going to talk about what if we have decay? What would that look like? A certain isotope has a half-life of 10 hours. If the initial mass of the isotope is 18.2 milligrams, what is the total mass after 50 hours? My suggestion with word problems is always read them twice. First time, just read it through to see if it makes any sense to you. Second time is we're going to go back and really see what we know. Whenever you see the word half-life, it's telling you that the rate is 1/2. Whether you refer to it as 0.5 for the R or 1/2, it means the same thing. Now, with every half-life, it's going to provide you with an amount of time that this occurs. So this particular one is 10 hours. So down here, I know that the R is 1/2 or 0.5, and how often the occurrence, it occurs every 10 hours. That's what I know. The initial mass, the initial weight of this is 18.2, and I want to know the total after 50 hours. So I want to know the total, and I know the initial is 18.2. I know the rate is 0.5 or 1/2. Remember that this rate always will go with a specific occurrence. This is 10 hours, and just like that, the total always is going to relate to the top number. We want to know the total after 50 hours. I'm simply going to plug it in. Again, we know 50 divided by 10 is 5, so I'm taking 0.5, raise it to the 10th, and then multiply by this outside number. First do this, and then take it times the outside number. So I come in here, I'm going to change this number to an 18.2, change this to a 0.5, and up top, I know that number is going to be 5. Okay, I'll just make sure I type this all in correctly. It looks good. Now, if they say, I'm going to write down exactly what I see first of all, and then we're going to talk about rounding. If I click here, I can see I can get an exact. So this is exact. There's no rounding involved. So if they provide you, and they don't say to round, then I want the exact one, and make sure to label it with units. I want the exact. Now, what if they told us, and let's just practice rounding. What if they said round to the nearest hundredth? Well, this is hundredth. I look behind and I go, okay, 0, approximately 0.57. What if they said round to the nearest thousand? Okay, look at the thousand and look behind. Approximately 0.56. Again, look behind. 9. Okay? So depending on how they want the answer. This is rounded to the hundredth, to the thousands, and this is the exact. It's precise. It is not asked you to round. You provided me with a precise answer. Let's do the same thing, and now let's switch it up. Let me just cross out some stuff to make, for purpose of saving time. Let's say we have an isotope and the half-life is 8 hours. Let's go with the initial mass of 3.4, and let's go with after 32 hours. I would like you to press pause, and I would like you to work on simply setting up the equation with this information. Press pause, come back in the next 30 seconds or 45 seconds and see if you have set up the equation correctly. I know I have a half-life of 1/2 that occurs for this particular problem every 8 hours. I know the initial is 3.4 milligrams, and the total that I'm trying to find is going to correspond with 32 hours. So this is what I have. I could plug this in to decimals and to get an answer. Make sure to label it again in terms of milligrams. Let's talk about what you know. When you see this, you think, okay, this is pi. Now, what is pi? Is pi a variable or is pi a numerical value? And I found in my previous class that most students know that it is a numerical value. And in fact, like, you're almost ingrained to think that it's 3.14 something, right? It's an ongoing irrational number, has no pattern to it, the decimal never stops, but we know that that has a numerical value attached to it. Well, today I'm going to introduce another numerical value. It's not a variable, but yet it is a letter, and it is an italicized E, and it stands for Euler's number. And Euler's number is approximately 2.71. And when they look to define different scenarios and real-life problems, they have found that this number consistently occurs. This consistently occurs. All right. It is also the base of the natural logarithm, which we'll learn about later on. But right now, all you have to know is that E is not a variable. E is not a variable. E is actually a number. It is irrational, and just like pi is irrational, 3.14 goes on and on. Euler's number, this E, is 2.71, and it goes. I'm going to start by talking about, let's analyze some graphs that have E's in them, that have Euler's numbers. So let's go with g of x equals, I don't know, 1/3 e to the x plus 4 plus 2. Now, before I do anything else, I think that it is important for us to just take a second to kind of reflect upon what does it look like when we take and we transition or shift exponential graphs. So let's come back to this in 1 second. Let's just first look at this. Let's say y equals AR to the x. Okay. So this is just the basic graph of exponential, right? Basic graph of exponential. And there's a couple different things we can do. First thing is this number outside. If this number outside, like this is what we've been learning all along, dating back to August, maybe even you learned this freshman year. If this number is between 0 and 1, it's between 0 and 1, not equal to 1, not equal to 0, we say that there's a compression. And if this number is greater, so if this number is greater than 1, we say there is a stretch. Remember the number with the x is going to describe a horizontal shift. And it always lies to us. Okay, so up here, if I did like an x minus 2, well, naturally we think shift it left 2, but it's actually lying to us. We're going to shift to the right 2. And any number down below, such as like a +5, this is going to be a vertical shift. Remember, vertical shifts tell the truth, and horizontal shifts are going to lie to us. So this is an example right now. If we go from this basic form, and I say, all right, I want us to look at this particular graph. Let's go with this one. And I want us to compare it from the basic y equals 2 to the x. So this is the parent function. This is the parent function. Okay. Now I've put something in front, I've put something up above, and something in back. And if you had to describe in words, the order you describe in doesn't matter. What can we say? Well, I know that 1/5 is between 0 and 1. So I would say that this particular graph is going to compress vertically by a factor of 1/5. Okay. Notice that we now have a -3. It's going to shift to the right, it lies to. It's going to shift to the right by 3. And it's going to shift up, or vertical shift up 4. Let's do one more. Let's say this time we have this one. And this is the parent function. And now to that, I've put this. And if you had to describe this time, we would say a stretch, vertical stretch by a factor of 3, stretch by a factor of 3, shift to the left 2, and shift down 7. Okay, so now we're going to take that, just a little bit of a review, and we're going to come back to this problem. I don't have too much left, so stick with me here. The goal of this particular problem will be, can you plug this into Desmos, and then can you analyze it correctly? So we're going to analyze it in a couple different ways. So the first way we're going to analyze this is we're going to state, what is the domain? What is the range? Are there any vertical asymptotes? Is there any horizontal asymptotes? And is there any intercepts? Those are the 5 things. So I'm going to literally press pause for 1 second. I'm going to come up here and put this into, I'm going to put this, actually I'm not going to press pause. I want you to see how I'm plugging it in. That's probably going to be valuable to you. So I'll come over here. Remember, this is going to be an equation, so it starts with the y equals. And I'm going to put 1/3 in parentheses. And then I'm going to start with e. Remember, e is no longer ever considered to be a variable. It is now considered to be a number, specifically Euler's number. Now, to get up top into the exponent position, we're going to do a to the b. And you do have to put parentheses around. So it's going to be not just x plus 4, it has to be parentheses x plus 4. I'm going to use the arrow to come back to the same level as the e, and this is what I have. Now, if I am able to zoom out, you can see what this looks like. So I'm going to do just a very basic picture of what that looks like. It'll be easier for us to look here at this graph. Very, very basic. I'm going to come back to it so I can see what it, oops, sorry, I'm going to come back in here. Okay, so it looks something like, I got to see up here, whoa, way up here. Okay, so I can see what that number is. Give me a second to write that down. Okay, and if I come back here, and see that number there is 2. Okay, so I'm going to come back here and I'm just going to do a brief picture just to make it easier for us to talk about. Okay, so let's start with the easier parts. This is exponential. There's no limit how far it goes to the left, and there's no limit how far it goes to the right. Yes, it's going up, but it's going up at a diagonal position. So as it goes to the right, it's being pulled up. That's how we have this diagonal. So the domain is -infinity to positive. Now, there is something to talk about here. Let's see if I can grab a highlighter. There is a hidden asymptote. We will never, ever, ever have vertical asymptotes. We will never have vertical asymptotes with exponentials. But you will have horizontal asymptotes. You will have horizontal asymptotes. And so I can see that this horizontal asymptote is achieved by looking at this last number. So y equals 2. How do I know it's y equals 2? Because it cuts through the y-axis. So what's happening here with the range? It never actually, even though it appears, it never actually touches at 2. Never touches. It approaches, but never touches. And for that reason, it's parentheses 2 raised to infinity. So as low as it goes, this doesn't mean it touches, it approaches, and there's no limit how high it goes. Again, there is this hidden horizontal asymptote. It cuts through the y-axis at y equals 2. X equals 2 would be wrong, y equals 2. There's never any vertical asymptotes. And there is an intercept. Now, is this the x-intercept or y? Well, there's no x-intercept, so this is the y. So it does have a y-intercept of 0 and 20.199. Okay, so I would like you to do the following. I want you to answer these questions: domain range, vertical, horizontal, and intercepts. These 5. Domain range, please write them down. Domain range, vertical, horizontal, and intercepts. I'm going to provide you with a different equation. Please do domain, range, vertical asymptote, horizontal asymptote, and are there any intercepts? Okay, put it on pause, please. Plug this in, answer, and then press play. So I'm going to talk through those 5 right now. This particular problem has a domain of negative infinity to positive, both parentheses on both ends of that statement. The range is going to be affected by what your horizontal asymptote is. Notice off to the side here, of the equation, it's a -6. Just to show you here, I could type in -6, and I can make that a dotted line, so that really kind of shows you where that is. Why is it not showing us there? Because it should be a negative. There we go. So I can see here that although it looks like it's touching, remember it's approaching that line, it's never actually touching. So what would the range be? The range would go from -6 to positive infinity. Again, parentheses on both because it never actually touches where there'd be a point of y equals -6. It approaches, gets closer and closer and closer as it goes to the left, but it never actually touches it. Vertical asymptotes. There will never be vertical asymptotes with exponentials. Horizontal asymptote, as you can see it off to the left of my screen, y equals -6. It's not x equals. Again, it cuts through the y-axis, so y equals -6. Intercepts. This particular problem happens to have 2 intercepts, and I can zoom in here. I simply click on the graph. I can see there is a y-intercept, and this problem has an x-intercept. I can click on it and can also see the x-intercept. What if you were given, this is a different problem, it's the last problem that we're going to analyze today for the review. What if you were given like 4 different graphs, A, B, C, or D, and you were asked to identify which graph models this equation? So what would be my helpful hint? Well, first I would go into Desmos, and I'm going to change this up. This was a 3, this was just an x, and this was a +1. As a reminder, anytime you put something up here, if it happens to have an x +1 or x +2, you got to put it in parentheses to keep it up top in the exponent position. So this is what I have. And if I had to somehow look at 4 different graphs that all had the same basic shape, and I had to figure out which one, on a multiple choice test, which one models this equation, the first thing I would do is I'd figure out what is the y-intercept. So I would go through all choices, A, B, C, and D, and anyone that did not have a y-intercept, in this case of 0, 4, I cancel out. Also make sure they have this same basic curve where it's going up as you go to the right. Next, I would look to see what is the horizontal asymptote. Well, I can see it looks like it's approaching. It looks like for this problem it is approaching 1. I know when you and I look it looks like a 2, but notice as you go up here they are going up. There we go. Looks like it has a 1, and I know that from looking back at the equation here it's a +1. So as I look at the 4 different options hypothetically, which one looks like it has a horizontal asymptote of 1? And then from there we're allowed to cancel things out to choose the right one. Now let's analyze this particular graph. I want you right now to write down what is the domain and range of this. Ready? Go. What is the domain and range of this particular graph? Okay, I will do the same, domain and range. So domain, negative infinity to positive. Range, although it approaches 1, it never actually touches it, and there's no limit how high it goes. Now, I don't really care for how it's written, but let's have you do this next. I want you to write this down as I write it down, please. Last part of today. So we're going to do the end behavior, but instead of doing the end behavior all at one time, they're going to do it in two pieces. So it's like, this is part A and this is part B. What does this mean? This means if I look to the very far right, one of three things is happening. The graph of the function is headed up, which would be positive infinity. It's headed down, would be negative infinity. Or it's approaching one particular number and getting closer and closer to that number. So let's look. As I go to positive infinity, what's happening? Positive infinity is way over here. What's happening? The graph is headed up. I can see that. The graph is headed up when I go to the far right. And for that reason, I would put a infinity or a positive infinity. You have to have the plus sign. It's not necessary. Now, what does this mean? As I go to the far left, what's happening? So if I go to the far left, I can see that it's getting closer and closer to this line. Now, what is the value of this line? It's y equals 1. It's getting closer and closer as I go to the right, to the line, to the value of y equals 1. So over here, I put in a 1.